Hello, guys. Welcome to Ramta Solutions. Today, we are going to look at the rate and extent of reaction. So, with this topic, we basically are calling it the rate of reaction. Okay. So, at the end of this video, we introduce what we mean by rate of reaction and how we get to see it maybe in our everyday life. And we will define what is this rate of reaction or what you call the reaction rate. And secondly, we're going to look at the collision theory. Remember, the collision theory basically tells you what needs to happen for a reaction to occur. Okay, so these are the three things that we're going to look at. So without any waste of time, let's look at it. So let's begin with the introduction. So for our introduction, I want you to consider a burning matchstick. Okay, I want you to consider a burning matchstick. And then I want you to consider an effervescent tablet dissolving in water. Okay, an effervescent tablet dissolving in water. And then I want you to consider an old car rusting. Yeah. Of course, this old car, we normally leave it outside, right? Yeah. Let me just say an old car rusting. So remember, all these are basically chemical reactions, all right? All these are chemical reactions. So this old car, because it's now outside and it's no longer covered, you will find that over time it's rusting. Over time it's rusting. Maybe you might not even see the rusting coming to an end in your lifetime. It might take years, all right? However, it keeps rusting. So I want to ask you, which process is faster, right? Which process is faster? Think about it. Which process is faster? This one is faster, and this one is slower, right? This one is slower. I do understand that with the effervescent tablet, it is a bit faster than your normal tablet, but I think your normal matchstick, if you burn your normal matchstick and dissolve an effervescent tablet in water, you will find that your matchstick is burning faster than your effervescent tablet dissolving in water, right? So now you are going to understand why these things so what causes these differences, all right? So basically, at the end of this topic, you're going to understand what causes these differences. Let me just call it like that. You're going to understand what causes these differences. What differences? The difference where the burning matchstick, basically the reaction completes faster than the old car that is rusting. In the same way, the burning matchstick is also reacting faster than the effervescent tablet. So we're going to understand what causes these. Okay? We're going to understand what causes these. So as you can see, I had said the burning matchstick is a faster reaction. The old car that is rusting, it's rusting at a very slow pace. So it's a very slow reaction, right? It's a very slow reaction. So basically, when we talk reaction rates, now when we talk, oh boy, let me change colors. When we talk reaction rate, all right, we basically are talking the speed at which a chemical reaction occurs. Okay, we are talking the speed at which a chemical reaction is occurring. Okay, at which a chem reaction occurs. Okay, so we are we are talking about speed at which a chemical reaction is occurring. Okay, so that is your reaction rate. However, for your definition in grade 12, you will have to understand that when we talk reaction rate, one, we will say it is the change in concentration, okay? Change in concentration of product or reactant, okay? Or reactant per unit time, okay? Per unit time, okay? So it is the change in concentration of product or reactant per unit time. Or if you like, you can say it is the changing amount of substance, okay, or the changing amount of products or reactants per unit time. It's still the same thing, right? So it's change in amount. So here, this means you can use the number of moles, right? This means you can use number of moles. Okay, this means you can use number of moles. So it's change in amount of product or reactant per unit time. Okay, per unit time. Okay, so what we are saying now is this. As you can see, allow me to call it rate of reaction. Let me just call it a rate of reaction. Okay, I will say to you, rate of reaction is initial concentration of a substance. Oh, sorry, final, not initial, because we said change in. So it's final concentration of a substance minus initial concentration of that substance, right? All over reaction time. Okay, all over reaction time. All right. In the same way, you can use final number amount of substance, which is final number of moles minus initial number of moles, right? Which is which is final number of moles. Okay, which is final number of moles. Okay, which is final number of moles. All right, so you can say final number of moles minus initial number of moles all over reaction time. If you are given concentration, you can say final concentration minus initial. If you are given number of moles, you can use final number of moles minus initial number of moles. Okay, and you will still be okay. All right, perfect. Perfect. So now this is the formula that we are going to use. Remember, I said to you, you can expand this formula by, you know what, let me remove these. Let me remove these lines. Okay. Remember, I said to you, you can use number of moles of a substance if you're not using concentration, right? You can use number of moles of a substance. Okay. So now this is the rate of reaction. So we're going to try some calculations, maybe some simple calculations where we calculate the rate of reaction. I'm still removing this. I don't like it. Okay, that's perfect. Okay, let me wait for it. Just want to make so many copies. Okay, perfect. So now we're going to do examples. So I'm going to try maybe 2 examples. Okay, I'm going to try 2 examples. Example 1 says, given 4 lithium in solid phase plus oxygen O2, in gaseous phase, giving us 2 lithium, giving us 2 lithium, lithium oxide in solid phase. Okay, calculate the rate of reaction. Calculate the rate of reaction. Okay, calculate the rate of reaction. Yeah, calculate the rate of reaction of lithium. Okay, calculate the rate of reaction of lithium if after 2 minutes, 4 grams of lithium has been used up. Okay, 4 grams of lithium has been used up. Okay, 4 grams of lithium has been used up. Okay, by the way, the molar mass of lithium is 6.94 grams per mole. Okay, I want to go back to the formula here. Remember here, the reaction time is in seconds. Okay, perfect. So, what we are given here is this. We are given the information that the time, as you can see, the time is 2 minutes. All right, the time is 2 minutes. 2 minutes is basically 2 times 60 seconds. So this is 120 seconds. Now, we are given the gram that has been used up. We are not really given the number of moles. Remember, we use the number of moles. So we will say number of moles, as we know, stoichiometry, is mass over molar mass. Right? Is mass over molar mass. What is our mass? Our mass is 4 grams. What is our molar mass? It is 6.94. Okay, so let's see. So what is 4 over 6.94, or 4 divided by 6.94? I will leave it to, let's say, 5 decimal places for now. Okay, because I don't want rounding errors. So I'm just going to say 0.57637 moles. Okay, so there's information here that has been used. They said 4 grams that has been used up. Okay, I want to show you something. This is your chemistry from grade 11. Remember what you're doing. You're saying amount of substance used, right? Amount of substance used is basically what is it? It's basically amount of substance initial minus final, basically, or vice versa, right? Or vice versa. Okay, so it's basically amount of substance initially minus final. All right, this is amount of substance that has been used, because in a chemical reaction you will start with, let's say you start with 0.21, right? You start with 0.21, and then because this is a reactant, at the end of the reaction, let's say you have 0.1, okay, 0.07, right? Yes, you ending with 0.07. So basically, N that is used would be N final minus N initial, right? What is this? This is 0.07 minus 0.21, of which the answer is negative, by the way. It's negative 0.14, right? The answer is negative 0.14 moles. Do not be surprised by the negative. It makes sense. The negative is to indicate that this is a reactant, so it loses substance, right? It loses substance, so it's okay to be a negative. All right, perfect. So now coming back here, we will be saying, so this means the number of moles that has been used up is 0.57637. Okay, now our rate of reaction, let's see, yeah, our rate of reaction, we will say, therefore, rate of reaction is N of lithium used over reaction time, right? Over reaction time. I do understand that the formula looks a bit different to what I gave you. It's okay. to also use it. Okay, it's okay to also use it. So what is it? The number of moles of lithium used was, let's see, what is it? It was 0. What is it? Where is it? Here is it. It's 0.57637. All right, it's okay. 57637 moles over, what is the time? The time is 120. Okay, the time is 120 seconds. Now let's get this. My answer divided by 120. What is our answer? Our answer is, I'm going to make it correct to 4 decimal places. It's 0.0048 mole per second. Can you see that? It's 0.0048 mole per second. Pay attention. I said I'm making it correct to 4 decimal places. It doesn't matter. If you like, you can also use scientific notation. Okay, you can also use scientific notation, maybe correct to 2 decimal places. It will be 4.80 times 10 to the minus 3, I believe. All right, 4.80 times 10 to the minus 3. Yes, it will be times 10 to the minus 3 mole per second. It's okay to be like this. All right, it's okay to be like this. As you can see, this is also okay. All right, perfect. Okay, let's try the second example. So for the second example, I want us to try this. Let's say, I will say 17 mole of magnesium oxide. Let me just write it. Of magnesium oxide, okay, was produced. Okay, 17 moles of magnesium oxide was produced in 63 seconds. Okay, in 63 seconds. Calculate the rate of reaction. Oh, I'm used to writing RxN. Let me just write reaction in full. Okay, so let's see. What information do we have here? We have number of moles produced. All right, number of moles produced. And as we can see, initially it means there was no magnesium oxide. So number of moles produced is 17 mole. Now, what is the reaction time? The reaction time was 63 seconds. All right, so the rate of reaction will be, it's still the same. It's still saying a number of moles of magnesium oxide produced, basically, right? So I don't even have to write that formula. So you can simply say this is 17, or let me just write this. Number of moles of magnesium oxide, I believe it's like this. Is magnesium in group 1 or 2? I don't recall. So magnesium oxide. Come on, guys. Okay, I don't recall. Okay, let me just write magnesium oxide. Yeah, because I don't recall. Number of magnesium oxide produced, all right, over reaction time. Right, over reaction time. So now what do we have? The number of moles of magnesium oxide produced was 17. What is the reaction time? The reaction time is 63. Now, what is our rate of reaction? Oh, by the way, it's 17 moles over 63 seconds. 17 over 63 seconds. What is this? This is 0. I'm going to make it to 2 decimal places. This is 0.27 mole per second. This is the reaction rate. So, to explain the reaction rate, remember we said it is the rate at which a reaction is occurring. So you can imagine this. In this reaction of magnesium and oxide, we are forming 0.27 moles of magnesium oxide per second. So it means in 2 seconds, we will have formed 0.54. In 3 seconds, just like that. Every second, 0.27 moles of magnesium is forming. Okay? Similarly here, every second, 4.8 times 10 to the minus 3 mole of lithium is being used up per second. Okay? It's being used up per second. All right. Perfect. So now let's see the second item. We basically are covered with this and this because we introduced what it is and we also defined the rate of reaction. Now let's look at collision theory. Okay, let's look at collision theory. So we now looking at collision theory. Okay, we're now looking at collision theory. So collision theory says for a reaction to occur, I'm going to look at it in different ways, but I'm going to take this one here. For a reaction to occur, please allow me to write reaction in this way. For a reaction to occur, reactant particles must collide, okay, with correct energy and orientation. Okay? Reacting particles, let me say this, reacting particles must collide with correct energy, okay, with correct energy and orientation, okay, and orientation, okay. So basically here we are seeing three things. For a reaction to occur, particles must collide, but they shouldn't just collide. They must collide with correct energy. So this is condition 1. Condition 2, with correct energy and with the correct orientation. So these are 3 conditions, all right? For a reaction to occur, reacting particles must collide with correct energy and the correct orientation, okay? And correct orientation, right? And correct orientation. So what is happening is this. Here's a tip that I'm going to give you. So basically, collisions, okay? Collisions provide energy needed for the reaction to occur. Okay? Provide energy needed for the reactions to occur. Energy needed. Provide energy needed for the reactions to occur. Okay? For the reactions to occur. Alright? While we are on it, not all reactions, okay, not all reactions will basically result, not all collisions will basically result in a reaction, okay? Not all collisions will result in a reaction, not all collisions will result in a reaction. All right? So remember, for a reaction to occur, this means you producing one or more products. All right? So we're saying not all collisions will result in a reaction. All right? So basically, we are saying a collision which result in a reaction, let me write it properly. A collision which result in a reaction, right, will produce a product, right? A collision which result in a reaction will produce a product, and this collision, we refer to it as an effective collision. Okay? All right. A collision which result in a reaction will produce a product. right, will produce a product. This collision, right, this collision is called an effective collision, right? It's called an effective collision, right? It's called an effective collision, okay? It's called an effective collision, okay? This collision is called an effective collision. Which collision? That collision that results in a reaction that will produce a product, okay? That collision that will result in a reaction that produces a product, we call it an effective collision, okay? So what we are basically saying that a reaction will only occur if the collision is effective, okay? A reaction will only occur if the collision is effective, okay? If the collision is effective, that's the only time that a reaction will occur, okay? So the collision theory also gives us some things. What does it tell us? The collision theory, what it does, it basically says something about the speed at which a reaction is occurring, okay? So basically, reaction rate, okay, is proportional to, I think you have an idea now, those factors that were mentioned by the collision theory. We're mentioning them now. Reaction rate is proportional to 1. Basically, we can say, let me just say number of collisions per unit time, okay? Number of collisions per unit time, okay? Number of collisions per unit time, of course, between reacting particles, okay? Between reacting particles, okay? Between reacting particles. Secondly, the reaction rate is also proportional to that portion of collisions, right? So what I'm saying is reaction rate is proportional to the fraction of effective collision, okay? To the fraction of collisions that are effective, okay? To collisions that are effective, okay? To collisions that are effective. So this is what the collision theory tells us. Remember, this collision theory, we said, it said that for a reaction to occur, reacting particles must collide with correct energy and correct orientation. So basically what it does, it says to us that these collisions are providing energy needed for the reactions to occur, and we know for a fact that it is not all collisions that will result in a reaction, but there is a portion of collisions that will result in a reaction, not just a reaction, but there is a portion which will result in a reaction that will produce a product. Some collisions are weak, right? So if those collisions are weak, that means somehow the energy is less than the activation energy, right? These are the things that we will be looking at later, right? So I repeat, a collision which results in a reaction will produce a product. Of course, this collision, we call it an effective collision. If a collision does not really result in a reaction, no product will be formed, right? So it will have insufficient energy to form a product, right? Remember the conditions for collision theory. 1, reacting particles must collide. They shouldn't just collide. They must collide with correct energy, and they must collide with the correct orientation. But when we say correct orientation, we are not just saying orientation just for the sake of it. It is correct orientation at the moment of impact, okay? With the correct or the right orientation at the moment of impact. So these are the conditions of your collision theory. And these reasons given here, we're going to use them in our factors affecting reaction rate. We're going to use these reasons a lot in the next video. So stay tuned, guys, and I will see you next time. Next time, we're looking at factors affecting reaction rates. So from me, this is it for now. See you next time, and bye-bye.